Hey class, and welcome to a short help video on the second workshop problem. I've gotten questions from a few people about this one, partly to make sure you understand the diagram that you see here, as well as just kind of what's going on. But basically what we have in this problem is a before and after picture showing a falcon fending off a raven. All right, so these small falcons, as you can see, they only weigh about 600 or have a mass of about 600 grams, can fly after and chase off ravens. And one of the ways they do that is by actually like dive bombing and crashing into them to kind of chase them away. They tend to be quicker and more maneuverable, and so they can kind of do that. And so here we see that you have a falcon flying due south, so straight down in the picture here. The falcon is labeled here. It's the smaller bird at 20 meters per second, and it collides with a raven that's flying at 9 meters per second due east here. As a result of their impact, all right, as you can see, the falcon is going to bounce off, moving both north and a little bit east after the collision. As you can see here, 30 degrees sort of east of due north, and then the raven is going to be moving south and east after the collision here at some angle theta east of due south. And so what you're asked to find in this is what is the final velocity or the net velocity of the raven after the collision, as well as the direction, so that angle theta that it's moving at, and then lastly, how much energy, if any, is lost during the collision. So first of all, this last question implies that maybe using conservation of energy is not the best way to go. Instead, you should think about looking at conservation of momentum. So just to remind you, conservation of momentum, we use P, right? That means the initial momentum is equal to the final momentum before and after the collision. Here we have an isolated system, two birds in the air, so yes, momentum should be conserved. But since momentum is a vector quantity here, we're going to need to break this down into x and y components. So we're going to need to look at, say, conservation of momentum in the x direction, so the initial momentum in the x equals the final momentum in the x, and then the same thing in the y, initial momentum in the y equals final momentum in the y direction. Okay, so to figure that out then, what that really means, if we write this out just in variable form, okay, in the x direction we would have the mass of the falcon times the initial velocity of the falcon in the x direction plus the mass of the raven times the initial velocity of the raven in the x direction, and that would be equal to the same variables in the final. So the mass of the falcon times the final velocity of the falcon in the x direction plus the mass of the raven times the final velocity of the raven in the x direction. And you could write out the same equation for the y direction. But for now, I'm going to just start with the x. So to get going, you really need to identify your variables, right? You need to identify initial and final velocities for each of these in the x and the y direction. So let's say we want to do the falcon. So the initial velocity of the falcon in the x direction, well, that's just 0 meters per second. He's not moving in the x at all. Let's see, the final velocity of the falcon in the x direction, well, that's going to be his final speed, which we're told that's 5 meters per second, right? So that's going to be 5 multiplied by, that would be the opposite side here, right? If we broke this into components, so that would be times the sine of 30 degrees. The initial velocity of the falcon in the y direction, well, that it's straight down at, let's see, 20 meters per second, so that'd be negative 20 meters per second. And the final velocity of the falcon in the y direction, well, that would be, let's see, he's going positive, so 5 times the cosine of that angle, 30 degrees. All right, so that's just for the raven, or excuse me, the falcon. Now we can do the same thing for the raven, so maybe I'll switch colors. So for the raven, the initial velocity of the raven in the x, well, that's the entire 9 meters per second. And then the initial velocity, or excuse me, to stick with the same pattern, we'll go back and do the final velocity of the raven in the x. We don't know. The initial velocity of the raven in the y direction is 0. And the final velocity of the Raven in the y direction, we also don't know. In fact, these two here are the two variables we're trying to figure out. And then we can put them together to give us the net velocity and the direction. So now let's go ahead and kind of fill in what we have here. So going back to our equation for momentum, the initial velocity of the Falcon in the x, that's 0. So we're left with the mass of the Raven multiplied by the 9 meters per second. And that's going to be equal to the mass of the Falcon. I guess I could put the numbers in if we want, but I'm just showing you partially to help you visualize, times the 5 sine 30 meters per second, plus the mass of the Raven times v final of the Raven in the x direction. And so what you can see here is you know everything except for v final of the Raven in the x. So you can actually solve from here. V final of the Raven in the x direction equals some number. You can then go back and do the same thing in the y direction. So let's say we decide to snag this, pop it down here. So again, we can do the mass of the Falcon times the initial velocity of the Falcon in the y, which is the negative 20 meters per second, plus the mass of the Raven times the initial velocity of the Raven in the y, which is just 0, so plus 0, equals the mass of the Falcon times that final velocity of the Falcon in the y, which is the 5 cosine 30 degrees, and then plus the mass of the Raven times that unknown final velocity of the Raven in the y direction as well. So once you have that all set up, then you should be able to solve for the final velocity of the Raven in the y direction. And so once you have that x component of the final velocity and the y component of the final velocity, you should be able to put those together to give you the overall net final velocity just using Pythagorean theorem. And you can find the direction using trigonometry and then do your calculations on the change in energy. Noting that, right, the only form of energy we're worrying about in this case, since we're looking at just before and after collision, is kinetic energy. So you can find the total kinetic energy before and after the collision. So I hope that helps you out. Let me know if you have any questions and have a box-worthy day.